In this lecture video, I will be going over the hydrohalogenation reaction of the alkynes. So the alkynes undergo very similar hydrohalogenation reaction just like the alkene. And now, mechanistically speaking, they're very similar. So if we were to understand how the hydrohalogenation reactions mechanism in the alkene work, then we should be able to apply that same understanding to figure out the mechanism of the hydrohalogenation reaction of the alkynes. And now let's talk about the products. There are different products that may be formed depending on the structure of the alkyne. Yes, whether we have a terminal or an internal alkyne would produce different types of products. But don't let this confuse or scare you, because either way, they make sense. So even though we don't have to really memorize this reaction right here, it is possible for us to actually figure out why one product will be favored over the other product, despite of what types of alkyne that we would have. And second, the different products can also be formed based on the amount of reagent that we use in this reaction. Because if we add too much reagent, it can react with the alkyne twice, and therefore converting that into the other products. And now let's talk about the reaction first. So let's talk about the terminal alkyne. What happens when we have terminal alkynes? Then when we do hydrohalogenation reaction of the alkyne, then we would observe that the major products is the Markovnikov product. And again, the Markovnikov product is the products where the halogen is added to the more substituted carbon, and the hydrogen is then added to the less substituted carbon. So in the case of a terminal alkyne, we can see that the two alkyne carbon are not equally substituted. This one right here is more substituted than this one. So when we were to add one equivalent of the of its X, where X can either be bromine or chlorine or iodine, then we would then see that in this case right here, by knowing that this is the Markovnikov as we've been told, then we can see that the hydrogen would then be added to this carbon, and the halogen would then be added to this more substituted carbon right here. And this would be the product right here, the Markovnikov products. Now, once the alkyne have reacted with the first equivalent of X, we'll be producing this product right here. And if we were to now have excess X in it, then we can see that this is very similar to an alkene, and we know that alkene would further react with the X further. So here in this case right here, so if we would have excess, this alkyne right here will react further one more time to now produce the germinal dihalide. And so please note that here in this case right here, that the halogens are actually being added to the same carbon in here. So the two halogens are added to the same side. So that's something about the regioselectivity that we need to be aware of, in which that we will be producing the germinal dihalide. And again, the word germinal dihalide means that the two halogens are added to the same carbon. And so let's now talk about the mechanism of this reaction, because once we see this mechanism right here, it's quite easy for us to predict and understand why the products are the way they should be. So here in this case right here, when we have the alkyne and we react with X, so we've seen already that alkyne are electron-rich functional group. So they're quite basic or nucleophilic. And in this case, we are adding to them a strong acid. So the alkyne will act as a base to come in and pick up the proton from X. And once this alkyne is doing a basic attack already, then now we can see that it will become a carbocation. And now we have two options. We can either have this carbon right here carrying the positive charge, or the other carbon carrying the positive charge. So those will be the two options that we have. Now, one option will be preferred over the other depending on the stability of this carbocation. And this carbocation right here is then referred to as the vinylic carbocation, because the carbocation locate on the vinylic carbon. And again, the carbon-carbon double bond are referred to as the vinylic carbon. So here in this case, we can either have this positive charge on this pole or the positive charge over here. And now let's take a look at these two other products right here. So here in this case right here, if the part of char were to locate on the most substituted carbon, this is now called the secondary vinylic carbocation, which is more stable than the primary vinylic carbocation. So therefore, the major product is the product where the part of char will locate on the most substituted carbon, this carbon in here. And once you have formed this intermediate already, the next step would then be the addition, the nucleophilic attack by the halogen. So the halogen come in and attacking our carbocation and convert this into this product right here. So if we were to have one equivalent of its X, we'll be forming this product right here, and this is the Markov products. Now, if we were to now have excess X, then we can see this reaction can happen one more time, in which the mechanism is as follows. So here in this case, the alkene would now act as a base, come in to pick up this proton, and now we will be producing this product. So we can now have a carbocation located on either this carbon or this carbon right here. So I'm going to draw out those two possibilities so we can see which one will be favored over the other. And yes, depending on which one is favor because of its stability, then that will be the major products right there, or lead to the major products. So we can either have the carbocation liquid on this carbon or this carbon right here. So here in this case right here, let's do the following. Draw the two structure. So we're going to draw this. So X right here. And let's say here that the carbocation, the hydrogen is now added to this hydrogen. Let's substitute the hydrogen. And here would then be our carbocation. So we can either have that, and this is the new hydrogen. So let me change this to a blue color. So that would be the blue hydrogen right here. Versus the other products where we can either have the hydrogen being added to the other carbon. So we can have these two types of carbocation right here. So between these two carbocation, which one is more stable? Whichever more stable, that will be the intermediate that it form, that it be in favor, and therefore it will lead to the more stable products or the major product. So here in this case right here, this is more stable. And the reason why this one right here is more stable is actually due to resonance. Because if we were to now put in a lone pair of electron here on this halogen right here, this halogen right here can actually donate electron in to stabilize that carbocation. Versus over here, then there's no resonance whatsoever. So therefore, this is more stable, and that's why that is the product that form more, and then followed by the attack of the other halogen. So the halogen will then come in. So let me now erase this error right here. So this halogen will then come in and now attacking that carbon. So in the end, the two halogens are then added to the same carbon, and that is why that we are producing the geminal dihalide. So here in this case right here, the product would then be as follows. And again, that will be the two halogen right here. So this is a geminal dihalide. As to what we have seen above here already. So again, if we were to have excess SS, its X, it will react with alkyne to convert this into a geminal dihalide. So that is how the terminal alkyne would react with the its X in hydrohalogenation reaction. Let's now talk about the hydrohalogenation reaction of the internal alkyne. So here in this case right here, the internal alkyne basically means that the two carbons are equally substituted, right? So therefore, then the products would then be basically a bit more messy right here, because now there's no selectivity. Because when we produce, either one of this carbon right here become the carbocation, then now they may be equally stable, and therefore we'll be forming a mixture of products. Okay, And so the geminal dihalide is still the major product. And again, geminal dihalide here means that the halogen are added to the same carbon. Yes, we do not form the products where we will form the vicinal dihalide. And a vicinal basically means that the two halogen are added to the two different carbon. But in this case, they'll be added to the same carbon. And so let's go look at the mechanism right here and in this reaction. So when we have one equivalent of X, we can either have the hydrogen added to the first carbon. Let's say this is the carbon 1 and this is the carbon 2. And so hydrogen added to the carbon 1 and the halogen and then added to the carbon 2. Or the other way, where now the hydrogen is then added to the carbon 2 and the halogen is then added to the carbon 1. So in this case right here, we can see that both of this product right here can be formed. And in fact, we can both either form the cis and the trans product as well. So both cis and trans will get forms. And this is why that this is quite a messy reaction right here, because it is producing a mixture of different products. And once we have produced this dihalide already, so this alkyne already, then if we were to have excess HX, then we can see this would react further one more time. And again, we then go through the same reaction mechanism. And now we can either have the carbocation right here or the carbocation right here. And in fact, the carbocation located on this carbon right here will be more stable. And again, that is due to the resonance effect from the lone pair electron from this halogen that donated in. And therefore, it will be the carbocation will locate on this carbon, followed by the attack of the other halogen. So therefore, we will then see that the two halogen will then be added to the same carbon. And similarly over here, so when we have this product right here, and if we were to now have excess HX, then again, this will come in, do a basic attack on here, and the major product will then be the one where the carbocation ion will locate on this carbon right here, where the first halogen locate in. And that again is due to the resonance stabilization. And followed by the halogen coming to attack this carbocation, and that's why that we still have the two halogen added to the same carbon. Okay, so there'll be a mixture of different products, and so but then in either products, then the halides are actually added to the same carbon, and this is why that we call this a geminal dihalides. And now let's talk about the hydrohalogenation reaction of the alkyne in the presence of a hydrogen peroxide, which undergo the radical mechanism. So we have seen already that when we did the hydrohalogenation reaction of the alkene, and if we were to have a small trace or a catalytic amount of the hydrogen peroxide or some sort of peroxide, then the anti-Markovnikov is in favor. So what happens if we were to do the same thing? So hydrohalogenation of the alkyne in the presence of the hydrogen peroxide or some sort of peroxide in the presence of lights, to basically force the reaction to undergo the radical mechanism. So what we have observed is as follows. The same thing would happen in the case of the alkyne, where we will form the anti-Markovnikov products. And again, the anti-Markovnikov product means the opposite, where now the X is then added to the less substituted carbon. So if we were to now have the terminal alkyne, and we now react this with one equivalent of HBr in the presence of peroxide and lights, then we'll be forming this product right here, where again, the geoselectivity is that the halogen is then added to the less substituted carbon. So in this case right here, they both added to the less substituted carbon, and the stereochemistry, they can either be E or Z. So here in this case right here, so this one right here actually Z, and this one right here is E. So we'll be forming both of this product, and this is the anti-Markovnikov product right here. And now let's try some of this example right here involving hydrohalogenation reactions. So let's try the first one. So in this first one right here, we are taking this reactant with its X. So what would be the major products? So here in this case right here, let's try this. So in this case, we can see that this is an alkyne reacting with excess HCl. So again, we will be forming the geminal dihalide where the two chloride would then be added to the same carbon. And here in this case right here, it would be added to the more substituted carbon. So basically the products would then be when we have, so this carbon, and now they be two chlorine, they've been added to it, and now the hydrogen are then added to the other carbon over here. So that would then be the major product of that reaction. And now 14, if we were to have this geminal dihalide right here, and now treat this with excess amount of sodium amine in the presence of ammonia followed by water, then what would be happen? Now, so here in this reaction right here, this is with the reaction that we have covered on the previous lecture already, and we can see that if we were to have a dihalide and we treat this with a strong base, we will be doing elimination reaction, or E2 reaction to be clear, to convert the dihalide into the alkyne. So in this case reaction right here, then the product that we would be making would then be as follow, the alkyne. So this addition and elimination reaction right here are the opposite of each other. If we start out with an alkyne and we treat this with its X, we'll be able to convert this into a geminal dihalide. Versus here in this case right here, if we were to start out with a dihalide reacting with a strong base, we'll be able to convert that back into the alkyne. So the two reactions are basically in the opposite direction. And now let's try this example right here. So here in this case right here, we do the same thing. So again, we have a geminal dibromide right here, and when we treat this with a strong base followed by water workup, we'll be able to make this product right here. So that will be the product of this reaction. And now let's try this number 17 right here. Suggest the reagent that will achieve this following transformation right here. So here in this case right here, we start out with having a dihalide where the two chloride are actually on this terminal carbon. And now we are converting this into a dihalide in which that now it end up on this carbon over. So basically the halogen have shifted from the terminal carbon into this carbon here in the on the internal carbon here. So what is going on here? So it seems that here in this reaction right here, we are taking this and we convert this into an alkyne, right? And once we have an alkyne already, and if we were to now do a hydrohalogenation reaction on it, then we'll be able to put the chlorine on the more substituted carbon in this case. So basically this reaction is as follows. First, we will take this and treat this with excess amount of sodium amine in the presence of ammonia, and that will basically will do an elimination reaction to convert this into an alkyne. And once we have this alkyne already, we will then treat this with excess HCl, and now this would then basically do a McCover addition where the halogen or the chloride here would then be added to this carbon right here. So following this second step right here, we'll be able to convert this into this, and now the hydrogen are being added to the less substituted carbon. So there you go. So that would be the set of reagent how we'll be able to make these products.